Hello, everyone. So this is Crash 1, a Starbucks story. It's a cooperation between Csaba and myself. I'm Gergely. You can call me Greg. It's hard to pronounce. I'm an independent bug hunter, and I used to be an ex-dev and sysadmin. I do a lot of that kind of work. And I have been doing vulnerability research in the the ASB platform, or program, rather. I have found 20 plus 0 days, and mostly I focus on logic bugs and follow-up research.
My name is Csaba Fitzl. I'm working right now as a macOS security researcher at Kanji, which is an MDM company who also does EDR. I used to work at OffSec writing a macOS exploitation training. I also do macOS bug hunting, now also part of the job. Have over 100 CVs now with Apple, and I'm really into trail running and hiking. So we have a really packed agenda for today. We will talk about a lot of stuff through a single bug. So let's kick in. We will mention StarBucks a lot. So disclaimer, Starbucks didn't sponsor us, unfortunately, although we are here for free coffee if they find us. So last year, we got together with Gergely when he visited Hungary, and of course, where IT people meet for a day, it's Starbucks. So we sit down and share some research ideas, some stuff where we sucked, and eventually we talked about a specific bug that both of us found, and both of us found it unexploitable. So what was that? So we found this OS Analytics helperd process, which is a helper daemon to write out process crash logs. Now, if a process is crashing and the process is run as the user, then the crash log will be written into the user home library logs diagnostic reports directory. And if the process was running as root, it will be written to the main library directory. Now, the problem we saw here was that this is a helper daemon which is running as root, but in case the process is running as the user, it will write into the user own directory. Now the user have full control over its own diagnostic reports directory. So we were like, okay, maybe there is some way to redirect that crash log or do something with that to achieve LPE. These were the file system events we observed when the crash log is written out. So we saw that the process is opening the directory. It's opening then the crash file. Because it's running as root, it will do a chown, so it will change ownership of that file to the user. And eventually, it will rename it from .process name time to the process name time. So it will remove the leading dot from the file name. But there were problems. So we tried like, okay, can we like symlink the directory or make some hard links there? But nothing really worked. It turned out that the process checked if the directory it's writing to is symlinked. Although if it was, it didn't error out, just went on. So we were not sure why the check is there. But yeah, it didn't really do anything. But then the file was opened with the OXL and OCreate flags, which meant that if the file exists, it won't be created. So you cannot place a file before or a hard link before the crash log is being written out. But the main limitation was the Sandbox profile of this process, which can be found here in that location. Basically, that profile didn't allow the process to write anywhere outside of those directories. So we were kind of stuck. And then a light came in because we missed one crucial thing in the Sandbox profile of this daemon, which was this. It says, if the process has an extension, Apple OS Analytics Sandbox read write, then it can read and write anywhere on the file system. So what is this extension and what we can do with that? So it's a Sandbox extension. Basically, a Sandbox extension on macOS is like a signed token in a C string format. Basically, it allows dynamic expansion of the process Sandbox. So let's say there is a given Sandbox process and there is an unsandbox process. the unsandbox process can generate a token, give it to the sandbox process, and basically grant it more access than it has. So typically, the way it works, again, we have the process A, which is unsandbox. It issues a token, send it to the process B, which is sandbox, over XPC or some other IPC mechanism. Process B has to consume the token, so it has to use it. If it doesn't consume the token, it will not take effect, and eventually process B can release the token. So these are some example APIs you can use to actually create a token, and there is the consume. That is a must. So what we did, we use this API, we issue the token for the root directory, which means it's valid for the entire file system, and we issued this token for that process, and we wanted it to consume. So only because we created the token is not sufficient. We need that process consuming it. So how we do it? It had a function to consume a token, so we reversed it. And sure enough, this function contained the sandbox extension consume system calls, which allowed it to consume the token, and eventually it also released the token. So it was actually quite short-lived. If we backtrace these functions, like where it is being called from, then we arrive to this massive XPC handler function. XPC on macOS is an IPC mechanism. You can send messages across processes in a well-defined way. Now, this XPC function was like a massive function. Even the decompiled code was like multiple hundreds of lines, and it would have been like a tedious work to actually fully reverse it and reconstruct the actual message, what you need to send to the process. So what we did, okay, this is like a legit message. Let's just debug that process and see what it receives when we crash a process. So we did this simple tool, crashed it, and sniffed the message. This was the message. Now, this is like big. It's a lot of work to reconstruct the C code for this message. So we just did, hey, ChatGPT, this is the message, do the code for us. And it's like 2 seconds, you get the C code for this entire message. So our plan was, we create a token, we can do that, and have the daemon consuming it when we send it over XPC. And eventually, we wanted to have the daemon creating a normal crash file just by sending him an XPC message. Now, we really badly failed at step 3. So we actually managed to get the token being consumed by the process, but it never created the file. We received some back-channel errors, which we didn't know what's that. So we had to do some more reversing. So it turned out that there is a function handling some back-channel stuff. And what it really did is it took the data writer endpoint from the message, and it created a new XPC connection to that endpoint and sent the file descriptor back to the caller. So what's the real purpose of this backchannel in like under normal operation? So normally when the crash is generated, report crash is the main process which is starting the crash generation. Report crash will call into OS Analytics helper D to create the crash file. OS Analytics helper D creates the crash file and sends back over XPC, over the backchannel, the file descriptor for the crash file for report crash to populate it with more data, like stack trace, virtual map, address mapping, and so on. And it has to return with 1. If it doesn't return with 1, the crash file will be deleted, basically. So what we had to do in our caller side, we had to implement the same logic. So we set up an anonymous XPC listener. We had to handle the callback and eventually return 1 to the OS Analytics helper daemon. So we managed to do all of that, which is great, but we are kind of still nowhere. But at least we can create a token, send it to OS Analytics helper D, and basically we could create a brand new crash log with XPC request. And if we symlink the directory at this stage, we could drop the file anywhere. So this was a good start, but we wanted to get a real privilege escalation out of this whole story.
Yeah, so this is my part. If you remember this, what is not visible here, but Csaba explained it perfectly, is that you only see the SRC parameter that goes into the rename system call. You don't see the DST, but basically what's happening is that the name will change very slightly by the dot getting removed, if I remember correctly. So like, what do you do with this? Well, this is basically an in-place rename. So it is fully equivalent to renaming a file at the same path. And intuitively, I talked to a lot of people. I believed that this was secure because surely the kernel would be smart, the kernel would be caching something, so this is not actually a cause for concern. And now the kernel cannot be smart for a multitude of reasons. One of these is that the file system structure might change in the meantime while the kernel is inside this system call. It's a very tight race, but it can be done. So whenever I see this, I'll immediately drop every other thing I was working on, because I do know that this is racy. So in this case, basically what I just described is happening. The kernel has to resolve the same path twice, and between the SRC and the DST resolution, you can switch the penultimate or whatever directory in the path, in the DST path, to a symlink. And what you will end up with, by the way, this is POSIX behavior. This is completely legal. This is how POSIX works. So fun fact for you, this works on Linux as well. Every rename is racy, so have fun. I found 0 days with this before. There are two prerequisites to this. One of them is, I called it nice to have here. The actual prerequisite is that I have to be able to control one of the path components going into the rename. In this case, it's the same, basically the same path leading up to the file name, so that's fine, we have that. The nice to have would have been, in a case of a perfect situation, is that the DST file name is being controlled, because in that case, I totally control everything. Now, we do match the prerequisite here, but we do not have the nice to have. So unfortunately, we do not have file name control, which is really gonna nip things in the bud. However, do notice that the target runs as root. Now, to win a race like this, we can be clever or we can be brute force. I'm not a particularly clever guy, so I usually go with brute force, because brute forcing is easier to write, easier to do, more feasible and more portable, generally speaking. It has two prerequisites, again, that are usually in place. One is that it has no serious side effects, and that includes being able to running the rename more than once, and that the actual triggering code that runs fairly quickly, because you want to try a lot of the time, or you want to try a lot. Both is true in our case, so this is erasable. The way you can solve this is you use the rename, the atomic rename that exists on macOS. It's rename at x mp, I don't know, this system call. And basically what you end up with is this. You end up with moving a completely arbitrary file that you totally control under any directory structure, except that you do not control the name in this particular instance. So this is an almost fully controlled file overwrite, which is pretty cool. It's a pretty strong primitive. However, the exploitation here gets a little bit tricky because you do not control the file name. So what could we do? Well, we can target something that some old school stuff. Most of you know a couple of these things. You would under Linux, you would basically overwrite some scripts. You would overwrite some config file, overwrite something else. But for that to work, you have to have file name control, which you do not have in this case. There are some directories that you can write stuff into. We'll get into that later. However, this is macOS. So the cron directory is TCC protected. I don't think it exists by default. And there's no scripts. And even if there were scripts, we don't control the name, again. But we do have some system services and sudo, and a lot of configuration likes, these days, modern times, likes to do this etc *.d directory where you can put a custom file to override one or two things in a sort of portable way, and it's very, very convenient for the system administrators to do this, and this exists in a lot of places. And the key thing here is that the file names do not matter at all. So we end up attacking sudo because we can just drop a file under etc/sudoers.d, and as long as the file is root owned and the other bits are empty for write in the basic Unix permission table, sudo is going to happily abide by it. Now, we can solve this any number of ways. We can open an FD, hard link, symlink, whatever. But I used ACLs for this because it's a very nifty little trick, and I thought talking about it would be fun. And also, it's really cool because you don't need to race. And it's very, very flexible because the ACL stays on the file forever. Now, in case you do not know what ACLs are, you can check the man page. Jokes aside, let's do a speed run very quickly. So it's a revoked standard, revoked POSIX standard, by the way. It got implemented anyhow, both on Linux and macOS, which is basically based on BSD. The implementations are incompatible, so this is absolutely useless for portability. On macOS, this is basically, as far as I could understand, exists to mimic some of Windows's behavior, because Windows does this sometimes that you can set inheriting ACLs on some directories, which is normally really not something that you would be wanting to do on a Linux system. So in this example, we can chmod a file called mydir at the end, so that we give the attacker user all sorts of permissions, all sorts of ACLs, including the file inherit and directory inherit ones, which means that it doesn't matter who drops a file into this directory later. It can be root. This can be done completely securely under normal circumstances using the basic Linux, macOS file permissions. This would be a completely secure operation, but with ACLs on, it's not. And wherever this file moves later on, you get to keep this control. So, and this is amazing. This is really amazing, because this is basically invisible to all user space programs, or at least to most user space programs. Because open source developers are not very keen on implementing platform-dependent behaviors. And in order to even get the list of ACLs, you have to call libc functions and do all sorts of magic. So most programs, including sudo, do none of this. So there was another problem that the file would have ended up getting CH-owned by OS Analytics helper-d. And we obviously need to retain the Unix basic root ownership over the file. We could have used ACLs, we could have used anything, but Csaba found a very cool way to sidestep all of this by setting a flag. So sometimes you don't have to work very hard. And to put it together, we basically wrote a Python and a trigger program in C. The trigger merely handled the Sandbox extensions, the XPC client part to trigger the actual vulnerability, and the callback or back channel part so that the call actually succeeds. That's really the hard part that was difficult to put together. And the Python part is pretty simple. It just prepares the environment and keeps running this trigger. Because we have no measurable side effects, nothing important is happening if we break it. You might have like a file somewhere that you didn't intend to write. Who cares? This is not going to be easily caught. It's not going to crash your kernel. It's going to be completely portable. So you can try as many times as you want. So that's exactly what we do. This is the exploit. I think I started it now. Yeah. So because it's a race, it still will take a little bit of time. Now we tried whether we can use sudo without a password. We can't. And we run the program. And it's going to take a little bit of time. This is sped up. I think it takes a couple minutes, if I remember correctly. Yeah, about that. Sometimes you get lucky, sometimes you don't. But eventually, you will succeed. And as you can see, now we get to use sudo without a password. Thank you. Are you doing this part?
OK, so we got a nice LP from this, but we wanted to take it further and actually use this technique to escape the macOS sandbox. I have one slide on this. So what turned out that talking to this XPC service to OS Analytics helper-d is restricted for the general Sandbox application, but any platform binary on macOS can talk to this service. So even if you are a Sandbox macOS process, you will be able to talk to this binary that's we can see at the bottom from the system Sandbox profile. So potentially system binaries, even if they are Sandbox, they can escape their Sandbox. So let's say if you find some code execution vulnerability in one of the system daemons and it's Sandbox, you can use this to escape its Sandbox. So Of course, if we are sandboxed, we cannot issue sandbox extension for OS Analytics Helper D, so we cannot do all these redirection trick, etc. But we can still use the library logs diagnostic reports directory, because that's the location where, by default, the process has access. Now, because we are not looking for privilege escalation at this step just to escape the sandbox, the general idea of escaping the sandbox, or at least one of them, is, let's say we drop a DMG file on the disk. DMG is a disk image, like an ISO. And if this DMG file doesn't have a quarantine flag, which means, let's say it won't be sandbox, let's put it in a simple way, then if you open this DMG file, and if you have an application in that disk image, you can start that application without any system prompt or gatekeeper or whatever, and that application can be an unsandboxed application. Eventually, we also found that XPC, this XPC message will allow us full file name control, and because we get a file descriptor through the back channel, we can also fully control the content of that file. So the idea was that we drop a DMG file in the diagnostic reports directory. Through the back channel, we overwrite it with the actual disk content, and then open this DMG, and the DMG will have an unsandboxed application, and we just open this application, and it will run unsandboxed, basically. And this is a video showing that. Before I started, again, because we are talking about only system processes, what we choose, we installed a screensaver. A screensaver is basically, think of it as a dylib or bundle DLL on Windows. It's basically a library which is loaded by the screensaver daemon, and it's executed. And screensaver is a sandbox, very heavily sandboxed process on macOS. So what we plan here is actually, so installing the screensaver, it will be run. It will escape the sandbox by opening an unsandboxed application, and that unsandboxed application will run the previous privilege escalation exploit. So we go from a standard sandbox user code execution into like a full unsandboxed root. And we also open a remote shell there. So we installed the screensaver. If you just click on that, it's already executed. So now it's running. Now we see the disk being mounted and the exploit application being started. Now this is actually the privilege escalation part, and we have a shell listening. We get a callback, and it's running as root. So the patch.
Oh, do you want to talk about it?
Okay, I can. At least the first part. So Apple took a few steps on patching this vulnerability. First one was they put an entitlement check for the XPC part. So basically, whenever you wanted to communicate with OS Analytics Helper D, you have to present like an Apple private entitlement. Now, you cannot just assign an Apple private entitlement to your process, even on macOS. If you do so, your process will be killed instantly before being executed, so you cannot run. So this is actually a good check. It means you can no longer call OS Analytics Helper D through XPC. And the other fix was they fixed the rename part, changed it to rename at XNP system call, and they put the rename no follow any flag, so they don't follow any symbolic links from now on, and actually this is the way to fix it. Yeah, so they fixed it both ways. Unfortunately, we had a collision on this bug with someone, and we came second, so we never get anything for this, but at least we have a nice talk from it. That's it.
Thank you.